Hi, everyone. Today, I'm going to do an interview with a compiler developer at Groq, and I'm pretty excited to get right into it. Hi, Gautam. Did you want to introduce yourself to the audience?
Hey, as Dr. Raku said, I'm a compiler engineer at Groq. We work on running LLM models at light speed, and I work on building the compiler that enables that to run on our custom hardware.
For sure. And Gautam and I had actually spoken a bit previously, and I was pretty impressed by the depth of his knowledge in model inference in general and how to speed it up. So I really wanted to record this video. Yeah, Gautam, can you tell us a bit about how model inference generally happens today in regular companies?
Hey, so I guess it depends on what perspective you're thinking about it from, but I'd like to start by saying that most people, when they think of model inference, they're thinking of an API. So that's the kind of first thing to know. You, as a customer of this API, you go send a request, you submit a bunch of tokens, submit some other parameters, and then you get back a response. So what's happening in the back end is that quite often these models are run on specialized hardware. It's fairly common knowledge that the most used specialized hardware are called GPUs. And the kinds of programs they're good at are these very computationally heavy programs. So something that involves a lot of like math, like a lot of adds, a lot of multiplies, a lot of subtractions, that kind of thing. So matrix multiplication, that's one of the like fundamental primitives of all these like LLMs, and GPUs are really good at it.
When I think about model inference, I think about the queries that the user's typing going to a machine that probably has lots of GPUs plugged into it. And I think I've heard that they batch those queries together so that, you don't just have my one little query going in, but maybe there's a few of them going all at once. And then you're trying to maximize the use of the GPUs essentially. But that's obviously a pretty high level picture. Can you paint a little bit more color there in terms of how standard inference would happen today, like an OpenAI cluster, for example, or something like that?
That's actually like a really good point. That is how they use GPUs a lot. And that kind of comes to the limitations of GPUs as well. So I'll try to explain what I mean by that. So how a GPU does inference is basically to have all the weights of the model stored in something called high bandwidth memory, which is a component of a GPU. It's a very expensive component of a GPU, but as you can tell by the name, it's a lot of memory of the order of tens of gigabytes. I don't know exactly how much, it depends on the configuration, tens or more of gigabytes.
So for the GPU, all the memory is considered high bandwidth memory, right? Like I'm sure there's a cache hierarchy, but like
right.
If it's an 80 gigabyte GPU, then all 80 gigabytes are like high bandwidth memory, right?
That's right. Yeah. All of those are high bandwidth memory. But like, I guess it's very important to think about the caches on chip as well, because that's the memory that you need, that you actually use when doing the compute. So how GPUs work are this approach where you like take the weights or the activations and the activations generally, both things. You take them from the kind of memory space, which we call HBM. You load it onto the GPU like compute portion, the compute die, and then over there you load it into the caches, and there you like do the computation, you write the result back to the caches, and then you write all of that back to HBM.
So I know for a CPU, for example, you would spend a lot of time actually waiting for the right piece of data to come from memory to the CPU, do the computation, send it back. They call it like I'm blanking on the name now, but like CPUs are getting a lot faster than memory bandwidth was getting, right? Like 20 years ago.
That's right. Yeah. Like in the last like 40 years, what's basically happened is that memory has gotten a lot slower than compute. Or I guess the good way to think about it is compute has gotten a lot faster than memory. But in all of these processes, the bandwidth is not the actual matrix multiply, even though it seems like that's the hard part. The bottleneck is the bandwidth of HBM, which is low compared to how much computation you can do per unit time.
So I assume for a large language model that's stored in a GPU, the weights are like the only thing that's stored in memory. So every time you fetch something, you're fetching different weights. It doesn't sound like a very efficient use of the caching mechanism, right? Because the cache can only save a small portion of the memory, and it's probably not whatever you accessed most recently.
I'm sorry, I didn't fully understand that. Like the weights are not the only thing pulled from the memory. Like you also have the actual model activation, like the query that gets transformed over the course of the model. That's another fairly big piece of a fairly big chunk of memory that you need to store in HBM and then move to the caches. But you can't store all the weights in memory in the caches, if that's what you're asking.
Right. And I guess because the cache is most useful when you're re-accessing something you've accessed before, the activation is not very cacheable either, I assume.
Yeah, but I guess like we're not going into the details of how the cache is actually used because it is useful to store those things in the cache still. Because when you're doing a matrix multiply, for example, if you think about how often a column of the weights is used, if you think of like the activations as the left side matrix and the weights as the right side matrix, you see that one column of the right side matrix is used by all the rows on the left, right? So it is still useful to cache them. That property still remains. And like when in LLMs, generally the weights are localized to a single layer. So like if you have the weights of a certain, like the weights at the top are not the same as the weights at the bottom. So like it's not the case that if we load the weights on top onto the compute die, that we just want to leave them there forever and like do nothing with them. Like that's not going to give us an advantage. So the GPU, there's nothing wrong with the GPU like offloading that, except for the fact that it's really slow to offload it. That's the expensive part. It's not that we're going to reuse that later, so we want to keep that. It's just that it's going to be very expensive to move it back and forth.
Gotcha. Yeah. Obviously, if you fetch something from memory, you're going to do probably a few computations on it before you send it back. So obviously, the cache is still going to be useful there. You said that the topmost layer, for example, is different from the bottommost layer.
Yeah.
So do they take a lot of care to lay that out carefully in the GPU memory so that like, the weights for the same layer are close together and that sort of thing? Or does it not really matter at that stage?
I think it's in HBM, it doesn't really matter how you lay them out, right? So you like in HBM, it doesn't matter. But once you like, if you have like weights that are for operations that are right next to each other, there is this thing known as fusion of kernels. So I should say what a kernel is. Like all of these GPU operations are written in a language called CUDA, which is a proprietary language that NVIDIA maintains. So you write down how a matrix multiply, for example, you write down how it would work in CUDA. And then you compile it, and then you're able to run it. All right.
For my viewers, if you watch my channel, you may know that I did a video on CUDA last week, so you can check it out here if you want to see that little setup there. Totally unintentional, but thank you. Sorry, carry on.
Yeah. So I'm glad that you did that last week because that gives some context into what this is. So if you write a CUDA kernel for just a single matrix multiply, and then you write a CUDA kernel for the matrix multiply after, then there will be no kind of sharing of cache space between the weights or the activations of the two. Kind of the kernels are kind of the smallest unit of compute. And so you load up a kernel, and then it loads all the weights and activations. It does its thing, and then it sends the data back. Then you do the thing for the next kernel and so on. But like, as we said before, like this transferring is expensive. So a major optimization that GPU kernel writers like to do is try to write fused kernels that kind of go deeper down that like layer stack. So instead of just doing one layer, maybe you do some part of the next layer. And like a layer is more than just a matrix multiply. I just called it a matrix multiply, but it's generally more. It's matrix multiply. There's often like some like softmax style operation and stuff like that. Again, I'm not a model expert, so I'm talking very loosely about what these things are, but like, yeah.
It's still very interesting. I think of a CUDA kernel as like an individual program that is doing one computation. So the way you described it, it sounds like there are multiple kernels. They don't really share much because they're independent. And this one is written to use the cache in a certain way. That one's written to use the memory and the cache in a different way. And obviously, if you combine them a little bit, like you fuse them together, then you're going to get better performance because it's like, oh, I don't have to fetch this thing from the cache. It's already there. So I knew that. And it's kind of intuitive in the name, fused kernel. But it's very interesting to me that they're actually fusing it in the sense of taking the computations one layer further in the network. That makes a lot of sense.
That's right. Like if you think about, if I have two CUDA kernels, I need to do like one above and then one in the middle and one after, 3 transfers to and fro HBM, right? But if I only have one CUDA kernel, I just need to do 2. And if the name of the game is reducing these HBM transfers for GPUs, then you can see why fusing these kernels would be really advantageous.
Very interesting. And about how many layers do deep neural networks have these days for, large language models?
I'm not sure I can characterize them in terms of number of CUDA kernels. Again, I should say that I'm not a CUDA kernel expert. This is all just because I work in the industry. But like, I think like Llama 3.18b has something like 10 decoder layers or something. And then Llama 3.170b has 80 decoder layers. I'm more certain of the second number. I'm not so certain of the first one. So Llama 3.180b has 80 decoder layers, and a decoder layer is actually like not that small. It has probably multiple CUDA kernels. So you can think of like of the order of hundreds of times that you're like transferring data to and fro HBM. So yeah, that's again, this is all order of magnitude estimates. Yeah.
One thing I don't quite understand is, let's say you just have one input coming into the neural network, like one token or whatever.
Yeah.
that information can quickly spread throughout the network. So it's not like one source node impacts one node in the next layer, which impacts one node in the layer after that. So how are you handling the kind of fan out of that information if you're trying to, fuse together different layers of the neural network?
I mean, it can all be thought of as like a DAG of computation. So like I'm describing everything as if it's a chain, but like similar principles apply if it's like, as long as it's linearizable, it's kind of the same thing, right? Like a DAG is just something that it takes a little longer to write down as a chain. So there are costs associated with it. Like in particular, when we talk about the Groq architecture, I think we could like discuss how if you have this like expansion of memory, it is we have to solve for the problems of expansion of memory. For a GPU, it doesn't matter so much because you have a ton of HBM lying around. So if you have like a point where the memory expands a lot, you can just write all that stuff, write all the like extra stuff back to HBM and you're fine. So GPUs are generally not going to be overloaded an amount of memory because they have this huge tank of memory available to them, which as we'll talk about at some point later, at Groq, we don't. Yeah.
I mean, that's been the one and only selling point of more recent versions of GPUs, essentially, right? Is, look, there's even more memory, so you can fit even more model weights, and I suppose also activations, which
that's right.
Sense.
Yeah, just having more memory makes it easier for kernel developers to just make sure that their models are able to run. Yeah.
One more question about that then. So how fast is it to transfer stuff between GPUs or between the GPU and the CPU? Because I know historically that had been a big bottleneck, but you also hear about these like high bandwidth interconnects like NVLink that's supposed to hook together two GPUs. So if you're a kernel writer, can you actually go, I'll grab that from this other GPU, or I'll grab that from CPU memory, like main system memory, or is that just not possible?
It is possible, but especially with the new like Blackwell architecture, I think they have like the smallest unit is like two GPUs that are connected together by like some super high speed like connection. But I'm not aware of the exact numbers, but I know that it's in general slow compared to HBM and definitely slow compared to like what we do at Groq.
Yeah, that makes sense. It's usually a hierarchy, right?
Exactly. It's like you could think of it as like bigger and bigger like memory hierarchies, I guess. Yeah.
Exactly. Like on a computer, you have like CPU registers, CPU cache, main memory, disk, network, and everything is just slower and slower. So
exactly. So it's similar, and obviously, the memory on cache is the stuff that's like put into like that's associated with the compute portions on die, like on the like thing on the like wafer that had the same electronic circuit etched on it, and then HBM is like connected to it during the packaging stage, and then the other interconnects are done after, and so on. Like it's again, I'm not like a networking expert, but yeah, like thinking of it like a huge hierarchy of caches makes a lot of sense to me.
Right. So let me try to replicate that for GPUs. So for GPU, there would be registers in the individual CUDA cores, and then there'd be caches, probably different levels of caches. And for GPU, it's programmable, right? Like you can actually decide what goes into the caches.
Yeah.
Right. And then after that, you have the HBM, the high bandwidth memory. And if you want to go to something larger, you're either talking to another GPU, which is one level up, or you're talking to the CPU, which is probably like two levels up because you have to go through the main system bus.
Yeah. And GPUs are generally, they were not designed for low latency. They were designed for high bandwidth. That's kind of like a subtle distinction for people who are like actively working on those. But yeah, so GPUs are great at doing, and this goes back to what we were talking about earlier, like why do they need to batch? So all of this stuff, like any single component is slow, but like you can pump a lot of data through these things at the same time, if that makes sense. So like GPUs can only achieve a certain amount of latency on like LLMs because of all these problems. But if you don't like batch, then what you're going to do is you're not going to get much utilization out of your GPU, and you're going to have spent all that money on your GPU for nothing. So in order to get the most return on investment from your GPU, the cost of doing one inference is kind of the same as the cost of doing 4 inferences, for example. That's how I think about it. So you batch them. No one inference is going to be super fast, but all 4 of them will come at roughly the same time. So you can do okay in terms of cost. That's how people use the GPU generally.
Before we move on to Groq, can we just talk very briefly about how floating point precision actually impacts this? Because we've heard about, back in the days of graphics, you would do 32-bit computations pretty much. And then now they have FP16, FP8, even FP4.
Yeah.
Can you talk a bit about that?
Yeah, for neural networks, it seems like precision doesn't matter all that much. Like at the training level, it matters a lot. So generally, training is done at FP32 because you really want to be careful with your weights during training. But during inference, people use a lot of tricks to speed up computation and save memory. So you can like increase, if you like reduce your weights and activation size from FP32 to FP16, you can see quite quickly how you can like double the amount of activations you have. Or also, you can also double the amount of weights on your GPU cache. So you can also make things faster. Same with FP16 to FP8 and FP8 to FP4. And people have done all kinds of crazy things to be like, I think there's like 3 value LLMs now, which have ternary value LLMs, which are like 1, -1, and 0, and they still work pretty well. So again, nobody really understands how LLMs work in terms of like the specifics, but it seems like we can afford to lose a lot of precision on the weights. And yeah, so because of that, GPUs have all kinds of like, I think Blackwell has FP4, and in fact they quote their like max whatever amount of compute in FP4 specifically. But yeah, like FP8 has been supported for a while, and FP16, and for training FP32 as well.
I didn't realize actually that in training you do want that extra precision and you keep it around.
You do,
But
yeah.
that makes perfect sense because you're making small tweaks to the
Exactly.
to the weights as you see each data point, basically.
Exactly. You can't afford to lose that precision during training. But during inference, you know the weights, so you can kind of just like, it seems like, I mean, this is just purely because of like experimental results. It seems like you can just squash the precision and just like it still works because I guess the argument is that the models are super over parameterized basically. So, like any individual weight doesn't matter so much. Yeah.
Cool. Is there anything else you wanted to talk about the general GPU ecosystem or whatever?
No, not really. Yeah.
Cool. So let's move on to Groq. Can you tell us a bit about, I mean, you mentioned it at the beginning, but, just tell everyone again a bit about what the company does and how it looks different from GPUs.
Yeah. So Groq we have designed our own hardware to run LLMs. And actually, it's not just LLMs. The company was started in 2016, end of 2016, by a bunch of engineers who founded the Google TPU team. And our CEO, Jonathan Ross, is one of them. He's still around. And from the start, they were very keen on building hardware specifically for AI inference. Back then, the models were different. I think ResNet 50 was probably the most inferred model around. ResNet 50 still used a lot for lots of things. But yeah, I think the key idea is that they were always focused on the inference market because they believe that once you train once, I mean, you don't train once, but you train roughly once and you do inference all the time. So if you think about it in that sense, the inference market is always bound to be bigger than the training market. And that was like a very like sharp insight in my opinion. I joined much later, but like I was really like convinced by their vision, of their technical vision, and as well as their like business vision. I can go to the technical details right now if you want, but like at a high level, we get rid of HBM. So like I've talked a lot about HBM for good reason to contrast the GPU architecture with our architecture. We don't have as much kind of like just HBM, like memory lying around associated with each chip. We have much less memory, but all of that memory is much faster. So we focus on latency, not bandwidth. And that's why we provide like a really cool real-time inference that you can kind of feel the kind of like user interface difference if you like go to our website versus go to OpenAI or like any of the other GPU users. So yeah, you can go to groq.com and check us out.
So cool. So you guys are replacing the GPU as the accelerator that's used for inference.
That's right.
And you don't care about training. That's a whole set of different trade-offs and everything,
Yeah.
but you're really focused on inference. Is that right?
Yeah, that's right. Yeah, we talked about how training requires completely different precision, but it also requires very different memory characteristics. So everything I talked about earlier with HBM and stuff, but also with training, like latency doesn't matter. You don't care if your training job takes like 20% more time. It just doesn't affect you that much. Like it's going to cost you 20% more. But whereas with inference, it really matters because somebody is on the other end of the API and there's a real person trying to get an answer back to try to see what's happening next. Or in some cases, like especially have you seen the new OpenAI model, like the strawberry thing? They do a lot of repeated inferencing. They do a lot of like search and inference time. So with that, like I think that like validates this idea that fast inference really matters.
Yeah, I mean, OpenAI, the model 01, which as of recording this video actually came out yesterday.
Yeah.
They're doing a lot of inference, right? Like you said, they're parallelizing the inference. They're doing a lot of search for possible solutions. And then they're going, this one looks best. Let's report that and use that.
Exactly.
And so when they look to scale this in the future, they're probably going to scale it by adding more compute, by adding more inference compute.
By adding more inference compute, exactly, not more training compute. So that's, I think, validates the vision of like fast inference being really important.
Yeah, I mean, when we hear about all these AI data centers,
Right.
A lot of my viewers really liked to hear about the Stargate data center, right, which is being built by Microsoft. These are all for training, right? They're actually single purpose build. They're like, we need to train a model of about this many parameters and this much resources. So let's build a data center just for that. So how does it look for inference? Do they build data centers explicitly just for inference? Or is it more like, they just come from a cloud, they rent the machines from the cloud and they just rent more machines as they need them? And so it's really the cloud providers that are building out general inference capacity.
So as of right now, GPUs aren't specialized for inference versus training. So once you do use the GPUs for training, you can just, once you decide you have less training load, you can just take some out of the training set and just like move them to the inference set. We are building data centers specifically for inference. And I suspect other people will start doing that soon, but you can look it up. I think we have a partnership with like someone in Saudi Arabia where they have a lot of like solar energy to build out inference data centers. And like the cool thing about building it out even somewhere far away from like maybe where the most use is in North America or even in Asia or something is that the amount of data sent across the network is really small, like with LLMs, right? Like you're sending like 1,000 words or 10,000 words, which is very small compared to like an image. So like inference, we are building out inference data centers. I suspect other people also do that for GPUs. It might even be possible that GPUs try to kind of move towards inference specialized GPUs at a certain point.
Yeah, it's very cool. And when you think about it, one of the main reasons that we have data centers like close to users is usually because of latency issues.
Yeah.
When you're doing an LLM query, it's not going to take like 100 milliseconds. It's going to take longer than that.
Yeah.
So the added latency of like sending information across the continent, like it takes about 60 milliseconds, I think, to cross the United States from coast to coast. So adding 60 milliseconds to a web page load can be like, it just means your customer is going to go away. But if you add 60 milliseconds or 100 if you're going to, Europe or something like that, it's probably not the end of the world. So yeah, I can see that. That makes a lot of sense. Move the inference compute to where it's most cost effective to run it rather than having it necessarily be really close to the consumer.
That's right. Yeah, that is how we're looking at it. Yeah.
So you said Groq is building their own inference data centers. Is that your main market? Like you're not selling chips directly to consumers, but rather it's like a cloud environment?
We're building data centers in partnerships with other entities that have access to energy and capital, because those are very big inputs to these data centers. In order to sell inference, we at the moment, I don't think we're directly focusing on the direct hardware sale market because there's so much demand for inference. And so it just makes sense to like sell it directly because we have the expertise in managing these things. They're well designed. They can be managed by other people, but there's just so much demand, so we might as well supply it.
Is your hardware sort of compatible with regular motherboards? Like, is it just a PCIe device like a GPU?
That's right.
Or is it?
Yeah, just a PCIe device. You can just plug it into a regular motherboard.
Okay. But yeah, I think going the cloud route or partnership route and building these data centers where there's money, power, that makes perfect sense.
Yeah, like we should talk about how our hardware works or like what makes it, like I briefly talked about the fact that it doesn't have HBM, which is kind of one of the defining features of the hardware. So because of that, like even though it is pluggable into a regular motherboard, if you just have one of these things, it's not as useful to run like LLMs because you would have to use it very much. You could transfer stuff over PCIe, like very much like you might over GPU HBM, but that's going to be pretty slow. But we are able to use our hardware in like much more interesting ways because like we're focused on the on-chip compute and like large amounts of on-chip cache memory, right? We don't call it a cache actually because it's not a cache. There's no like hierarchy. All the memory is uniform and it's all static RAM. So like for users who may not know, like there's like two types of RAM. There's like static RAM and dynamic RAM. So HBM is dynamic RAM. Like even the GPU has lots of static RAM on the chip itself. So we're focused on expanding out the like on-chip static RAM and having no dynamic RAM. Dynamic RAM, you can obviously have much more for less cost, but then you have all these complicated things associated with it, like moving stuff to and fro. Dynamic RAM is also dynamic in the sense that the amount of time it takes to load stuff off dynamic RAM is actually not known statically. It's something that's, that you can like get a signal for, but you can't actually know beforehand how much time it's going to take.
Let's just talk about dynamic RAM for a moment there. So
right.
That's like DRAM, and that's the RAM that's in a regular computer, like the CPU memory. And
that's
like
right.
you said, it's also for GPUs, like the high bandwidth memory.
That's right.
So from what I know about it being dynamic memory is because you have to actually dynamically refresh it. Like you put a value in, that value will stay there for a while, but it actually disappears after some time. So you have to like, I don't know, probably every 50 milliseconds or something like that, you have to like read the values from the memory and put them back in again, which is a huge pain. And you're also saying that there's like dynamic latency delays when you're trying to read from it, which sounds terrible if you're trying to get maximum performance out of your hardware. Anything else you want to paint in that picture, or like how it compares to static RAM?
No, I think you've done a great job describing it. That's the extent of my knowledge. I think someone with more of a background in electrical engineering could tell you exactly why you need to do the refreshing. Something to do with capacitors. Like I looked at the hardware circuit design recently, but I can't explain it well enough to tell you. But yeah, there's like capacitors versus just switches basically. Yeah.
So for static RAM, I'm assuming you don't have to refresh it.
You don't.
Is it volatile? Like if you cut the power, will the data go away?
Yes. Yeah, so that's the difference. That's like dynamic RAM is obviously very advantageous for lots of use cases. For like regular computing, it makes a lot of sense to have a lot of dynamic RAM available. Static RAM is like essentially just like any other on die component. It's any other kind of like compute component. It's like, yeah, you can only use it when it's on.
Okay, right, which is good. I remember that like non-volatile storage, which is basically like flash, is really slow. So you're getting something that's pretty fast, that doesn't need refreshing, that has more constant access. Does it actually sit on the same die as like your other stuff, like as fast as possible?
It does, yeah. Like we only have, it sits on the compute die. So we have about 200 megabytes of static RAM on a single compute die, along with like various different types of compute units. Yeah.
Very cool. You have less memory. It's static RAM instead, which means that if you have like a ton of model weights, you're either going to be transferring them back and forth, or you're going to be using a lot of your units, right?
That's right. So the approach we take is that we actually use a lot of singular chips, and we store all the weights in static RAM. And we have a custom networking solution to talk from chip to chip, which is actually low latency. So again, different from GPU in that it's focused more on latency than HBM, than bandwidth. So we spread the model weights across all of the chips, and then when an activation comes in, we load it up, and then we move the activation around all the chips. We do the computation, we collect the computation when necessary, and then we send back the result at the end. And the difference is we don't send back the result. We don't have this notion of kernel in the sense that, like I talked about earlier, you have maybe hundreds of accesses to HBM during a single inference compute for a GPU. We have none of that. All of the communication is happening within this large cluster that is just Groq chips and specialized networking across the Groq chips. There's no communication to DRAM or to the CPU that's connected or anything. That's it. Yeah.
So how does the latency compare for a Groq chip that's accessing its own static memory, static RAM, compared to like going across the network to a chip that's not that close to it, if you know what I mean? Is it much slower?
It is still much more expensive so I guess you can think about there is a little bit of a hierarchy in the sense that like if you have a chip that's like 10 hops across and they're all connected through each other, right? So obviously it's going to be more expensive to get the memory from that chip. The order of magnitude is 10 times more than just accessing local memory, something like that.
It sounds a lot like a NUMA architecture, like when you have a computer that has multiple CPU cores, multiple sockets, I should say.
Right.
That, they have some memory attached to this one, some memory attached to that one. And if one chip needs to access the memory that's actually like closer to the other chip, there's a substantial slowdown. I don't think it's quite 10x there because, you only have two sockets instead of like 10. But yeah, makes sense.
I think that the other difference in the Groq architecture, or the other like main feature of the Groq architecture that kind of mitigates some of these issues, is the fact that everything is known statically. Everything is known during compile time. So at compile time, we make the decision of which memory goes there. So we're able to really minimize the amount of accesses from, minimize the amount of these extremely slow accesses, because we solve this huge kind of like combinatorial optimization problem at compile time to make sure that all the stuff that needs to be as close together is as close together as possible. Obviously, you can't guarantee that everything is on the same chip because we have memory limitations for the same chip, like it's 200 megabytes for each chip, but you can try to like keep things as local as possible. And like this locality isn't like sometimes with like if you've ever done like performance optimization for CPUs, you would understand the notion of locality in cache locality. So like I write my program and then like I want to make sure that the two things I'm accessing like soon after each other are kind of in the same, like close to each other in memory somehow. But like that's much more of like a magic guessing game than what we have at Groq, in the sense that like we are able to know for sure that if two things are close together, we can put them in the same place because of this like whole static property of the whole system.
You start with a big DAG, like directed graph
That's right. Yeah.
of all the different computations that have to happen. And if it was CUDA, you would just be like, well, it looks like those can go together and those can go together, etc. But instead, you actually schedule in advance exactly where all these computations will happen across the entire network.
That's right. Yeah.
So your compiler has to decide where to place things, which, as you said, a big combinatorial optimization problem.
Yeah, it does have to decide where to place things.
And you also said 200 megabytes per chip. So if you needed like 100 chips or something in order to fit all the weights, would you hook that all up to one computer? Like, or would you need a lot of nodes to also store like 100 chips?
Yeah, like we don't hook them up to one computer. We have this notion of nodes, like a grouping. So we have, I think, 8 Groq chips to a node, and then we have racks of nodes, and then we have communication across racks as well. So that's how we do it. Yeah.
Oh, interesting. So it sounds actually very similar to a GPU setup, right? Like you can have about 8 GPUs per system because then you max out the PCIe bandwidth, and that's probably why you guys would do it too. But instead, where like a GPU-based system would have like one instance of the model per 8 GPUs or per 16 GPUs or something because there's so much memory. It sounds like you guys would have like only 1 or 2 instances of a really big model that's spread across everything, but it's just so fast and efficient at doing the computations that every user's query essentially goes through this one copy of the model.
Yeah, pretty much. So in a GPU, I think they actually like use even fewer GPUs to like, because they're not very good at scaling out. So they use fewer GPUs to run a single model. I don't even think they use 8 to run like most large models because they have 80 gigs of memory minimum lying around, right? So
I think GPT-4 uses either 8 or 16,
I see.
Like mixture of experts. But yeah, probably almost every other model would fit in one GPU. Right?
Right. For us, yeah, like you said, we distribute the model across these very large cluster of Groq chips, our TSPs. We also, like our LPUs, we have a few different words for them. But like, I think LPU is the word we really go with now, which is the language processing unit, to kind of really distinguish it from like GPUs, which were intended for graphics. We're like very specifically focused on low latency AI. But yeah, like if you think about the cost of running something, it's like there's 2 dimensions. There's the amount of like semiconductors that you're using, and that's like, you can think of that as the X dimension, and then there's the time dimension. So what you're looking at, the cost of running something is kind of the integral of your curve along this in this like 2-dimensional space, right? So the GPU curve, definitely they have very few chips, but the time dimension is quite large. And what we have is a lot of chips, but the time dimension is very small. So
basically what you're saying is there's no such thing as a small Groq cluster. You throw a lot in, but once you've done that, you get amazing latency, amazing
exactly, yeah. So we can, I mean, there are smaller models out there. There's like 2 gigabyte models and so on that we are actually amazing at, that like GPUs are never going to be able to compete with us at all and that kind of thing. But like when you get to these large models like 70B plus, then we have enormous clusters, but we are really efficient at scheduling the compute because we're able to do it statically, and we can like really push that latency down and not just get great latency, but also get great like cost effectiveness.
To me, that sounds incredible. Like normally when you're talking to the cloud, or at least I think about it as like there's thousands of computers out there and I just hit like 2 or 3 and they help me solve my query. But now you're like, there's thousands of computers out there and all of the computers helped me solve my query.
Yeah. Some people like to use it as like a negative against us, which is that, oh, you're using so many chips to do one thing. I think of it as like a huge positive because it's actually a really hard problem to solve, to like do the networking across all these chips efficiently. And we're able to do it because of the architecture decision to keep everything static. When you have like these dynamic components in your system, it becomes very hard to do optimization. So because of the static nature, we solve this huge problem and we put it all together, and then it works well. Yeah.
Let's talk about reliability for a moment, though, because if you have hundreds or thousands of these chips and every computation actually relies on all of them because some small piece of the model is put there, how do you fail over when one chip dies?
Yeah, that's a great question. And we're still learning how to run a cloud and like solving these issues in real time. But like I said, we have groupings of chips into nodes and so on. So if a node were to fail, we organize the topologies in such a way that we can fail over from nodes to other nodes. So within a single chip, we don't have failover at the chip level, but we have failover at the node level. So yeah, I'm not exactly sure when the failover happens. I think, I'll have to this is stuff we're still working out, to be honest, but we do have mechanisms for this.
That makes perfect sense, though, because if one chip failed, you would now have a node with 7 instead of 8 chips.
Yeah.
And then how do you fit that in? How do you schedule that? It's better to just take the whole node out, put a working node in, and then have it do the same work.
Yeah, we have these minimal units, and we can fail over across those minimal units. And then when a node fails, obviously somebody can be informed, they can be fixed, and then put back in rotation later.
Right. Yeah. I mean, that's my number one takeaway for really big data centers is that something fails all the time. You have so many computers and so many copies of everything.
For sure. Yeah. It's not something you realize when you're just using your one computer. But again, I've been working mostly on the compiler side, but as the Groq.com, the cloud service has become really popular, I've been kind of pulled into looking at some of the cloud stuff, and it's really interesting to see how often things fail. It's very new to me as well. Yep.
So let's talk a bit about your experience with the compiler there. I'm curious, first of all, if you guys use LLVM, the common framework for compilers.
We do, yeah. We use LLVM as our kind of base. We don't, LLVM is, I guess, specifically talking about the low-range CPU. We don't use that at all. We use a sub-framework or a framework developed within the LLVM kind of family called MLIR. And that came out of Google.
Machine level IR, right? I remember this.
It's actually called multi-level IR.
Or sorry, multi-level IR, yes.
Yeah, so
it's the one that's underneath the regular LLVM IR, is that right? Or I can't remember actually.
Yeah, I think so. LLVM IR is basically a specialization of MLIR. MLIR is not meant, LLVM is kind of very specifically meant to help you compile C++ to CPUs, and it has a lot of features for that, or compile general things to CPUs. MLIR kind of takes this in a different direction in that it instead of specializing, it generalizes a lot of the LLVM constructs and makes them applicable to other domains. So MLIR just gives you the ability to define your own dialects, your own kind of languages that kind of accurately capture your hardware's architecture. So it's a very nice framework. It's very much a framework. It doesn't give us much in terms of algorithms to solve the problems that we were talking about before, where to put what. But what it gives us a lot of is a language to define what our IR should look like. So for those who are not familiar, IR is a representation of a program. And a program for us is a Pytorch program. That's the kind of entry point. And the end point is machine code. So in the middle, you have multiple different things that you need to do to map Pytorch into machine code. And we have different dialects that help us do that. And the dialects are defined within the world of MLIR.
Gotcha. So MLIR is a framework for defining IRs in intermediate representations.
Exactly.
And you guys use it. So yeah, you go from PyTorch to machine code, but you have to solve the scheduling problem as well. So it sounds like you go from PyTorch to machine code for each node. Is that right? Or for each
That's right.
chip?
Yeah. For each chip pretty much. But yeah, for whatever are chosen minimum topology sizes, it could be a node, it could be bigger. PyTorch to machine code for every single one of those chips. And that includes the machine code to do the transfers from chip to chip.
I gotcha. Okay. So it includes the data for the actual weights of the nodes, I assume, because that would be put into the static memory.
Yeah. It includes the data. It includes the set of compute instructions. It includes a set of data transfer instructions. And yeah, that's kind of it. Yeah.
Gotcha. So it's it's like a multi-level compiler. Uses multi-level.
Yeah. It's an enormous beast. It does a lot of things. There's 3 or 4 different dialects. Probably won't go into that, but yeah.
Yeah, for sure. No, that sounds really cool though. So you guys are solving the inference problem from the ground up. You're taking the model weights and spreading them everywhere. You're statically compiling the graph. You're compatible with PyTorch, so you can do this in theory with anything.
Yeah, we are compatible with PyTorch. In theory, you can just give us a new model in PyTorch as long as you remove all the weird. We spent a lot of time removing the CUDA specific stuff from PyTorch, to be honest. If you wrote something in vanilla PyTorch, it's very easy for us to compile it. So yeah, once you give us a model in vanilla PyTorch, we have a flow that'll take a bit of time, but it'll pump out machine code for a given topology at the end. Yeah.
Any difference with PyTorch 2? I heard that they went a little bit further away from CUDA when they made PyTorch 2.
Yeah, I think PyTorch 2 is eager, as opposed to PyTorch 1, which was graph-based, right? So I guess we don't, I think we support eager mode in the sense that we are able to do it, but our compilation process is a little slower than the JIT compilation process they use within PyTorch itself, because I think in the PyTorch JIT compilation framework, I'm not 100% sure, but I think it's kind of a pattern matcher that looks for CUDA kernels or CPU kernels to run them against. For us, we're doing something a little different. So our compilation process isn't quite fast enough to do JIT just yet. So we can support eager mode, but that's not like our preferred mode of operation. We prefer something that looks like graph mode for us. So I guess like it also depends on like what your goals are when you're writing Pytorch, right? Like, are you trying to do like we're very much focused on the cloud service problem. We're very much focused on you do your development for starters on CPU, or even like you do your training on GPUs or like other whatever training frameworks, and then you have this model and then you want to serve it. This is a separate problem. And then you come to us with the Pytorch starter graph, like, and then we like are able to host it for you and then like, serve your requests really efficiently and fast. We're not currently focused on the problem of just like being able to iterate on your model in Pytorch directly accessing our hardware, but like that is certainly something that we would think of in the future.
That's very cool. I think, is there anything else you wanted to say about the compiler or how it works or your position there?
No, not really. It's just like a really interesting problem. Lots of like hard, like kind of CSE challenges. And just like a very unique compiler, different from most things because of like this property that everything is static. Whereas like if you think of like CPU compilers, they're actually like in some ways they're more complicated, in some ways they're more simple. They're more complicated because there's a lot of dynamic components. You can't do this like kind of reduction to simple operations in the same way. But also that makes it a little simpler because like you can just say, wait for this. You don't have to be like, oh, at what exact moment in time is this happening? Make sure that do this like synchronization. You don't have to do all the synchronization at compile time. You can like let the hardware do some of the synchronization for you.
Yeah, it sounds very cool. So I'm sure you guys could check out Groq and learn more about the company, but I just wanted to ask you specifically if there's any like large scale customers that you guys talk about publicly on your website or anything, so that we can get an idea of like the penetration of Groq's product.
I think we don't talk about large scale customers yet. We talk about a couple of things. One is that we have a lot of indie developers working on it, which was like the first constituency to kind of gravitate towards this because they were excited about the speed and able to build like fun apps on it that were not possible on like the OpenAI API, for example. We have, I think the last number is like 400,000 plus indie developers. We have some large customers that we're working with, but I don't think I'm allowed to tell you anything about that. And then I'm allowed to talk about our partnerships. We have partnerships in Saudi Arabia and I think in Europe with like energy-rich countries to build these data centers, and then like these inference data centers that we will kind of work together on and like sell inference on. Yeah.
I'm actually surprised to hear that you guys work a lot with indie developers, because I'm envisioning that like this is a very capital intensive system. But then again, if you have one cluster, you can give small pieces of it to indie developers. Is that kind of how
We're not giving them pieces of the cluster. We're abstracting all that away in just the API, right? So we build an OpenAI compatible API that a developer can just hit and get inference responses back. And the idea is that it's just that the latency of those responses is better than OpenAI. And it is, as far as I know. So I've seen like lots of posts on LinkedIn about people being happy with it. And yeah, once you have that latency, you can build cool new things with it. And I think obviously large companies are going to be hesitant to make that big capital investment to switch right away. But for indie developers, like when we kind of had a bit of our breakout moment like 6 months ago, they looked at this and they were like, cool, this is something I can actually use in my app. And then that's why we saw like a kind of organic gravitation towards our products. Yeah.
That's really smart to have an OpenAI compatible API, because everyone will develop against that, and then they'll do some searching, and then they'll learn about you guys and start using you, and then the product will become a little bit faster and maybe cheaper.
Yeah, that's right. Yeah, we have a great cloud team that's kind of like architected all that, and it's worked out really great so far.
I guess you guys have some internal, maybe like open models like Llama or something that's running there that people can select.
Yeah, we very much focus. I think we announced an official partnership with Meta on the Llama 3.1 release. And we have all the Llama models. Like I think maybe we've deprecated Llama 1, I'm not sure. But like we definitely have 3.18b and 3.17b available for general use.
That was not in my picture. I was envisioning that your customers would be very large, but like, once you have this working out, you can essentially serve it like
anything, like any API, to be honest, like any like SaaS kind of business. Once you have like all of the complex hardware stuff, like the serving process is simple, relatively. Yeah.
Sounds really cool. Was there anything else you wanted to mention about like, your customers, or maybe you could mention, you said the company's been around since like 2016, about how many employees you have, or like, how big is the company?
We're actually fairly small. At least I'd like to think so. For all the stuff that we do, we have, I think, 200 to 250 employees. The company's never really gotten bigger than that. Historically, we used to have pretty much just hardware and like software teams. And like when I say software, I meant like system software, like kind of systems programming stuff, like compilers, runtimes and stuff like that. We still mostly have those. The majority of people are still in that, but we also have a cloud team now, which helps us support all this, like all the customer demand. And I think we're hiring. So you should definitely check out our website and reach out to us if you have like things that, that you'd be interested in working with us on.
Yeah, it sounds very cool. A bit of a smaller company. And, Gautam got his employer's permission to come on here and talk about it, partially to, give more visibility to the company. So that's why we spent a little bit of time talking about that.
Yeah, it's a very open culture in general, I would say. There's lots of room for, writing. We've written multiple papers about our hardware. You guys can go check them out. They're like generally the papers are very technical. They're like published in ISCA, which is a major computer architecture conference. But yeah, and we have a blog, I think, where we publish some other stuff. You should check us out.
Yep, I know that conference. Definitely a top architecture conference.
Yeah.
I was just curious about your opinion about Cerebras, because I think they're probably a training-focused, specialized chip.
That's right. So Cerebras, I think, is one of our competitors. Historically, they've been training focused, but I think now they're like it is hard to break into the training market. So I think they've like kind of seen our success, and they're trying to go down the same path we've gone down, like by refocusing on inference. And they have some similarities in that they also have a lot of static RAM available on their systems, but they have different approaches to scaling out. And I think they've done some really cool work recently, but we'll see. We believe that our approach to scaling out is more flexible and better in the long run.
Yeah, I think Cerebras had these really mega scale chips, right?
That's
so
right.
We're trying to put as much stuff as possible into one chip, which probably is faster, but it doesn't scale very well, right? Because now as soon as you have like two of those systems and you're trying to like get them to talk to each other, you have a lot of problems to solve. Whereas you guys are starting with something pretty small, which you can kind of just stack it as much as you like.
That's right. And they also have, I think, I'm not a hardware engineer, but I've talked to hardware engineers in our company, and they have complex like hardware systems level problems to solve, because chip packaging is all designed for chips of a certain size, like because chips are like traditionally cut into a certain piece. Cerebras has to kind of solve all of the problems of like cooling, because these wafers are enormous. They generate enormous amounts of heat. I don't know what their energy efficiency looks like. It might be good. It might be bad. I'm not sure. But they are solving a whole different set of problems on top of also solving the hard compiler problems of like having to schedule. I don't think they do everything statically, but they do share some like parts of our approach. They have to solve the hard compiler problem. And like if you think about a wafer, like if you said everything's faster on a single chip, maybe a little true in that they don't have to go through the interconnects we have to go through, but they're restricted in the topology they're able to use. Like they have to use a two-dimensional grid, because that's the chip. It's a two-dimensional grid. Whereas we can connect our things much more flexibly. So for different types of models, we may be able to find topologies that are much faster than them, and they can't really change the topology as easily as we can. So I'm not sure that it's always going to be faster. We have a more flexible approach than they do. But yeah, obviously having everything on the same die comes with some advantages as well.
Yeah. And of course, the yield is the big problem, right? If you're trying to produce a huge die and there's one tiny flaw in it, the whole chip is useless. Instead of like normally they put, lots and lots of copies of a chip on one die, so that if there's some imperfections, you still get a lot of workable chips out of it.
Yeah, my understanding is that they actually try to work around the broken pieces at the compilation level, which is kind of cool. But like, not only is there a yield problem in terms of like things breaking down within, like I believe their actual hardware is like kind of rectangular or a square. You have to like embed a rectangle in a big circle, and you kind of lose a lot of stuff that way. Whereas if you have like these smaller pieces, you can find like you just get more yield just by looking at the like area ratios and stuff like that. That's my understanding.
Yeah, it makes perfect sense.
Yeah. But yeah, I mean, I think that they're trying to do what we do, and like they have also seen some success with their approach. But yeah, we'll see how it plays out in the long term.
Yeah. All right. Well, thank you very much for coming on and, having a chat. I think you had a lot of insights about, how these systems actually work at a really low level, how the data moves back and forth, how you can design the architecture to, really do inference a lot better. And I think that market is going to keep growing. So
yep.
I suspect you'll have plenty of business in the years to come.
Awesome. Thank you very much.
Thank you very much, Gautam. See you later.
Bye.
Thanks again to Gautam for agreeing to come on my YouTube channel. If you liked this video, please check out this previous one I made about how GPUs evolved from a graphics pipeline all the way to being AI powerhouses. Well, that's all I have for today. Thank you very much for watching. Bye.